start discussing representations of the supersymmetry algebra. And just as a preliminary for that, I thought that that it would be a good idea to try to understand these spinors a little better. So you might wonder what I mean by understanding spinors a little better. Of course, we've understood everything there is to understand about spinors, you might think, and that's true. But our discussion was very formal. Okay, it might be a good idea, I feel, just to get a little more hands-on, just to understand, what's going on. Okay, so let's start with the simplest dimension. Let's start with d equals 2. In d equals 2, if you look up our notes, I look up what we did, and I hope I'm saying this right. In Euclidean dimensions, there were no real spinors. Of course, d equals 2, firstly, spinors were chiral. So the question of reality we almost sort of ignored. But equivalently, in d equals 3, we said the spinors were in Euclidean dimensions were pseudo-real. Whereas d equals 2, we had real chiral spinors for Lorentzian space. And d equals 3 also, we had real, not pseudo-real spinors in Lorentzian space. Okay, so let's just see how this works. And also just explicitly work out the supersymmetry algebra in these two dimensions, just to see, really what's going on. Okay, so let's start with d equals 2. So our construction, if you remember, was gamma 1 is equal to sigma 1 and gamma 2 is equal to sigma 2. So let's start with d equal to 2 and start Euclidean. Okay, so we had gamma 1 is equal to sigma 1 and gamma 2 is equal to sigma 2. Okay. Well, that's great. When we had C, which was just sigma 2. Remember, C was the product of the last n matrices. Okay, so if we try to impose the reality conditions, that was psi star, psi is equal to C psi star. So now in this case, everything's very simple. Spinors are just two components. So let's write here psi is equal to alpha beta. Okay, so psi is equal to C psi star. What is this equation? Well, this means alpha beta is equal to, C is just 0 minus I 0, that's sigma 2, times alpha beta star. This is the reality condition we try to impose. Okay, but what is this reality condition? Well, let's do this matrix multiplication. This side is alpha beta, and on that side, what do we get? Well, on that side we get minus beta star, minus I beta star, and I times alpha star. Okay, and so this becomes the equations: alpha is equal to minus I beta star, and beta is equal to I alpha star. Now let's take complex conjugate of the first equation. So after taking complex conjugate, what do we find? We find that this is alpha star is equal to minus plus I beta. What?
Yeah, it's coming out.
Plus I.
Yeah.
Okay, but alpha star from here. But from here, alpha star is equal to minus I. Can't work. Okay. So you see what this was, of course, the integrability condition we imposed on the spinors, right? We did it twice, and so it came back to the same equation. We're doing the same thing here. All clear, right? Now let's see what happens when we go to Lorentzian space, where it should be. What was the difference? In Lorentzian space, we had gamma 1 is equal to sigma 1, but gamma 2 was equal to I sigma 2. So let's call that gamma 0. Right, we took one of the sigma matrices multiplied by I. Okay, now what is the reality? And what is C? Now C, we were free to phase with put whatever phase we wanted. It should be sigma 2. It's totally up to us. I'll choose C is equal to I sigma 2, just so that gamma 0 times C will be 1, rather than some I factor, which will be irritating. Right, because sigma 2 squared is 1. Okay, yeah. So now our reality condition was psi is equal to C times gamma 0 times psi star. Okay, once again we'll choose psi is equal to alpha beta. Okay, so we choose psi is equal to alpha beta and we get psi is equal to I sigma 2 times, I'll choose minus I, sorry, minus I sigma 2 times psi star, so that's equal to psi star. That's a reality condition. And in this case, this is simply the equation alpha is equal to alpha star and beta is equal to beta star. So in this case, the reality condition is simply that the spinors, the coefficients that appear in the spinors are real numbers. And certainly we can meet that condition, there's no problem. Right? So here we have nice real spinors. Okay, excellent. Let us also remember, okay, fine, let's move. Now, in this dimension, let's work out the supersymmetry algebra. Okay, so this Euclidean was just for fun. We're in Lorentzian space. So let me clear the Euclidean part. Okay, so we're in Euclidean, we're in Lorentzian space. Let me work out the supersymmetry algebra. So the supersymmetry algebra was Q alpha, Q beta. In this dimension, there was no omega because we had nice real matrices. Okay, and okay, what we had here was Q plus alpha, Q plus beta. Q plus alpha, Q plus beta was 1 plus gamma d 2d plus, well, d plus 1 by 2 times p slash times c. Like this was the dimension which spinors were real and chiral. Because they were real, there was no omega ij. And because they were chiral, there was this 1 plus gamma d plus 1 by 2. Okay. Then we had Q alpha plus, alpha minus, Q beta minus is equal to 1 minus gamma d plus 1 by 2 p slash c. Okay, and then we had Q, I'll write it the way he does. Q minus IL. Oh, sorry, what do I mean? C times Z. C times Zij. Hey, let's put let's put M labels here. N time. Let's put Ij labels here. And here we'll have an I and a J, and there was a Z, I, M. Right, this was the supersymmetry algebra we worked out for this dimension in general. But of course, in this dimension, all these are very big words. We can make them very explicit. So let's do that. Okay, first I'll give a name. The Q was a spinor, and I'm going to call it Q plus and Q minus. The components of Q I'll call Q plus and Q minus. First component is plus, second component minus. Okay. Now, one word for why this is a sensible thing to do. You know, what does plus and minus mean? Okay. What we had not worked out so far is what the chirality matrix is in this dimension. Okay. But the chirality matrix is clearly sigma 1 times sigma 2 times the right factor of I to make it square to 1. So it's sigma 3. Okay. So gamma P plus 1 here is simply sigma 3. Okay. Now, remember sigma 3 is the matrix whose eigenvalues are 1, 0, 0, minus 1. Okay. So if we label chiral spinors, as we always do, by whether they have plus eigenvalues or minus eigenvalues, okay, then the first component of the spinor is the plus chirality. And the second component is the minus chirality. Okay. So if we wrote down a spinor like this, these guys are Qs, and there may be many spinors. There are M such spinors, there are QMs, and here, yeah, okay. So if we write down more precisely, if we write down the mth chiral spinor, it looks like QM plus 0. And the nth anti-chiral spinor, it looks like 0 QN minus. I think I used IJ for that. Ith anti-chiral spinor, that's what it looks like. Okay, if we had a non-chiral spinor, there would be plus and minus, but this is really what I should say. Okay, fine. So what does this mean? So let's first just work out everything. Just work it out as matrices and then interpret what everything means. Okay, so let's work out the right hand side. One is 1 plus gamma d by 2. You see that this is the matrix 1, 0, 0, 0. Right, because 1 plus sigma 3, the diagonal components add in the top part, subtract in the bottom part, gives you 0. Just a projector onto the chiral subspace. Okay, now what is P slash C? That's interesting. Let's work P slash C out once and for all. And then we might need this. So let's work P slash C out once and for all. P slash C. P slash was P1 sigma 1 plus P2 sigma 2. Or P0 sigma 0. Okay, so this is 0, P1, and now our sigma was I times sigma 2, so that's plus. Right? Plus P0. And this is P1 minus P0 and 0. Please check. Because sigma 2 had a minus I in the top left corner, top right corner. And if I multiply by I, it becomes plus 1. Oh, I'm sorry. This is P slash. P slash is this. Now let's work out P slash C. P slash C is this times minus I sigma 2. So it's minus P0. Let's check. P slash was P1 sigma 1 plus P0 sigma 0, gamma 0. Okay. Plus. Okay. Just work it out to be sure. So that's 0, P1, 0. That's the first term. That's clear. Plus gamma 0 was I times 0 minus I P0 plus I P0, 0. Oh, that's what you're saying. That's what you're saying. But you know, our sigma matrix, now it's a question of which has upper and which has lower indices. So I will always take P to have upper indices, P mu, and P usually has, I want sigma to have lower indices. And sigma mu, you know, gamma mu we usually have put lower indices. So if by this definition and if by P0 I mean P upper 0, it's P upper 0 that's energy. So anyway, yeah, it's a matter of what you mean by P0. If you meant P lower 0, you would be right. Okay, thank you. What? Yeah, I mean, the usual convention is that P upper 0 is energy and P upper I is momentum. And let's stick to that usual convention. Okay. Of course, it's
fundamental fields are P lower and P lower means X are usually upper and you write for IPX. Then you set P lower and then that's it.
Yeah, you're asking whether what we call energy is P lower 0 or P upper 0. That's the question.
From this Q to power IPX.
Yes. Yes. Exactly. 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 Of course, it's a matter of convention.
Yeah.
But I think the usual convention is to take the upper label to be energy. Yeah. Okay, fine. So let's stick with that. No, that will matter. Okay, but let's stick with that. Okay. Great. So we have where were we? P slash. P slash was this, and we wanted minus I times sigma 2, which was -1, 0, -1, 1, 0. Right? So now let's work it out. P slash, just put this here. This we'll remember. So this guy times 0, -1, 1, 0. Okay. And this we get as P1 plus P0, 0, 0, and P1 minus P0. Minus P0 minus P0. Actually, that's important. That the P0 will come, the plus sign will be important. Yeah. Okay. Now, let us move on. Okay. So the right hand side of this object here was 1 0 0 1 0 times P0 plus P1 0 0 P0 minus P. Okay, what that 1 0 0 does is make it is equal to P0 plus P1 0 0 0. Okay, now you see in this case the point was here that PQ pluses were not spinors, they were numbers. Because they're just one number in our two components. So clearly we shouldn't have got a nice matrix structure here. We should have just got a number. The number we should have got only in the 1 1 column, which we're getting. And so this is telling us that somebody, if we need, will help me here. This is telling us that in this dimension, I can use from the right. Oh, I see. Oh, that's nice. So then this is no. I mean it. Huh? I thought couple it. Okay. Okay. So what this is telling us that Q plus M, Q plus N is equal to delta Mn times P0 plus P1. Right, that complicated matrix thing was telling us that. This clear? What? Alpha beta space, correct. Right? And the first alpha beta take plus or minus values. Okay, so when we write down a matrix here, this is plus plus, this is plus minus, this is minus plus, and this is minus minus. Point here was that we got a matrix with only component in plus plus direction, which had to have been right. Because once we put Q plus, it was a spinor with only plus at 0. Okay, so the fact that all this chirality was consistent, that if you took this through here, you got the right thing transposed. Okay, here we see in front of our eyes in a very simple way. So that kind of abstract kind of reasoning here is very simple. Yes. Oh, I'm really sorry. Here, I'm being so bad in notation. Upper plus.
Is it correct that it's a direct product of Q plus and Q plus?
Yeah, it's correct. It's correct. Q plus. See, what I meant here is the chiral spinor. So this, Sunil is right that we've used double notation because I've written a plus here as well. So what I want to say is that Q plus alpha is this spinor. Okay. Where this is Q plus without an alpha index, it's just a component. Okay, so Q plus and Q plus alpha are different symbols. Okay, and Q plus alpha means this. So if I have a Q M plus this. Okay, sorry for the poor notation. Okay, excellent. So you see this. Now you also see that if we take this equation, you see that the whole calculation will be the same except this 1001, 1000 will become 0001. You see that, right? Because the calculation of P slash C is not changed. It's just the 1 minus gamma by 2. Okay. And so we get Q minus M, Q minus N. This Ij, thank you. Ij, this is equal to delta Ij times P0 minus P1. You see that we get the minus P1 because we had this guy, so projects onto this guy. All this, all good. Okay. Finally, if we had a central charge, let's work this guy out. Okay. So this guy is C, which I think we take it to be minus I sigma 2. So this guy is 0001 times minus I sigma 2. So that's minus 1010 times ZIM. Now, before we start working it out, what should we have got? Yes, we should only have a minus plus index. Okay, which means second row, first column. Okay, and let's see if we're getting that. This is first row is clearly 0, second row, first column is 1. So we get 000 ZIM. Once again, these were never really spinor equations. Right? These were just components. Okay, and so we conclude. Now I'm clearing this and writing the answer. We conclude that Q minus I, Q plus M is equal to ZI. Okay, so shorn of all the verbiage, shorn of all the fancy, this is nice because it will also work for 10 dimensions, where this explicit form would be much more complicated. But in the 2 dimensions, this is what the supersymmetry algebra is. And you see, it's very similar to the supersymmetry algebra that we had in quantum mechanics. Remember, in quantum mechanics, we had M supercharges, okay, which squared to the Hamiltonian, each of which individually squared to the Hamiltonian, M real supercharges. Okay, here we have M supercharges that square to almost a Hamiltonian, sort of a light cone Hamiltonian, P0 plus P1. And then we have a certain number of other supercharges which square to another almost Hamiltonian, but a slightly different one. That is P0 minus P1. Okay, and then there is this interesting possibility of crosstalk between these two different kinds of supercharges. Okay, before we turn to the abstract analysis of representation theory, which we will turn to let's probably by the end of this lecture, let's also just work out one or two more dimensions, just to get a hands-on feel for what these algebras look like, what they actually sort of mean. Okay, first let's work out d equals 3. D equals 3 is very similar to what we had here. The big difference, of course, is that there's no chirality. Okay, so what was the supersymmetry algebra? The supersymmetry algebra, there's no plus and minus. That's q alpha, q beta. Okay, there's q alpha. Oh, something I forgot to say here was, and this is very important. Sorry, back to d equals 2 for a minute. Something I forgot to say here, and this is very important, is that the fact that our reality condition in 2 dimensions was that each component of the spinor was real will translate into the statement for operators that q plus I dagger, so q plus m dagger is q plus m. And q minus m dagger is q minus m. Okay, because when we go to operators, reality turns to dagger. Okay, so all of this is true, plus we have the condition, the hermiticity conditions, and this is of course very important. Q plus m and q minus I dagger is equal to q minus I. And so the fact, for instance, that immediately follows that the in this algebra, suppose we take the diagonal elements so that we get 1 on the right hand side from the delta n. Then what we've got is a product of the operator with its Hermitian conjugate with a factor of 2. Okay, and that tells us that that's of course a positive definite operator. So whatever appears on the right hand side has to be positive there. Okay, so this tells us that P0 plus P1 must necessarily be a positive quantity. It's also necessarily a positive quantity. In particular, P0 is necessarily positive. Okay, so this positive energy theorem that we had in supersymmetric quantum mechanics continues to hold true, but of course in a Lorentz invariant way. Okay, this is roughly speaking, the fact that you had P0 plus P1 and P0 minus P1 being positive, both of them being positive, will allow you to conclude that, of course, you could have done by Lorentz invariance, but anyway, that every energy, every possible energy, an energy is defined by a time. You can always boost your time. Somebody just told you energy along one time is positive. That doesn't guarantee that energy along some boosted time is positive. These conditions are the covariant version of that and are enough to ensure that every possible energy is positive. These are the extreme values of possibilities. If you boost time completely light-like, to go to the complete light-like in one way, you've reached P0 plus V1. Boost time to go to the complete light-like in the other way, you've reached P0 minus V1. Okay, and everywhere in between also you can easily check. Okay, so this hermiticity condition, of course, is going to play a key role in the representation theory of supersymmetry. The reality conditions will be very important for that. Yeah, good. We are imposing this on the supersymmetry algebra, and it's a consistent thing to do because we remember that the algebra was consistent with imposing these reality conditions. This is what we checked, right? We checked that if Q was Q dagger star, same thing, right? If it's a number, it's we checked that imposing the condition Q alpha is equal to C gamma 0 Q star was consistent with the algebra. Okay, so this is something we can do. It's part of our imposition in the algebra. the fact that Q was a real chiral spinor, this is what it means. What will, yeah, if it was inconsistent with the algebra, we would have found a problem. But Sunil is right that consistency is one thing and imposition is another. What we had done last time is to, in our abstract analysis, is to show that it's consistent to put these reality conditions on Q, and we are choosing to put these reality conditions. It's part of our specification of the algebra. Yes. No. Oh well, is it the only choice? This question. Right. Here, you see, this is the only choice that's possible with a simple supersymmetry algebra. When we study superconformal algebras, we will see there's one more choice possible. Okay. We will see this in much more detail as we go along our course, but let me say a few words about this right now. There are two ways to ask your question. One is algebraically. Okay, you could ask your question, Sunil could ask his question in the following way. He could ask, suppose I want to put a reality condition of the following form. Q alpha is equal to M is equal to, some matrix times other elements in the algebra. Okay, you could ask just this algebraic question. Is there any other choice that would be consistent with this algebra? In this case, the answer is no, because there are very few possibilities. Right? For consistency, Q has to be a linear combination of Q, because these are the only fermionic generators in the algebra. Okay, and M star is equal to this, and then what you're doing is trying to put some sort of reality condition on spinors. And the thing we did was basically explore the most general reality condition of spinors. So in this case, it's the only choice. Okay. However, when we study superconformal algebras, which we will do in the next 3 or 4 lectures, we will see that in superconformal algebras, apart from supersymmetry charges, there are also superconformal charges. And now there is a possibility of putting a condition, which is, roughly speaking, these superconformal charges are sometimes called S's. Roughly speaking, the kind of condition you could put is Q alpha is equal to S alpha star. And that turns out to be algebraically consistent. Okay, so that's the second algebraically consistent thing to do. Now, when two things are both algebraically consistent, could be that neither of them is implemented physically, or one of them is implemented physically, or both of them are implemented physically. Of course, nicest situation is when both of them are implemented physically. And we will see as we go along that the way it works is the following. Suppose we've got a quantum field theory, which is superconformally embedded, and you work out a Euclidean path integral. This one. Okay, this Euclidean path integral is just a path integral. There's no clear Hilbert space in this path integral. Always, as those of you who are in my string theory course know very well, always you get a Hilbert space from a path integral by slicing the path integral. Okay. Now, if we slice the path integral along lines of constant time, by which I mean we're going to analytically continue t to it. So that will give us a Hilbert space. Then you'll end up on this Hermiticity. On the other hand, if you slice the path integral in lines of constant radius, by which I mean that what we're going to do is to write r is equal to e to the power tau, and analytically continue tau is equal to it. Then you will end up with the other q dagger is equal to s kind of Hermiticity condition. So both are correct depending on what you're doing. Okay, because in a conformal theory, you can conformally map the plane to a cylinder. The second one is the natural thing to do if you're working on the cylinder. If you're working on SD minus 1 times time, then that would be analytically continuing the cylinder time. Okay, so both are correct. The second one happens to be more useful for many purposes. Okay, in some sense, both are correct. Correct answers to different questions. Okay.
So you can ask for any kind of real Hermiticity condition. There are too many constants, but you are saying these are the two physically relevant. hermeticity ones.
Yeah, about
So, I mean, are there another possibilities of time which we can take to quantize and then get another hermeticity concept?
I have never come across any. I remember that we tried to investigate the set of all possible consistent things.
No, but that we tried with the
This
dagger
it up.
conditions.
Yes.
How many dagger conditions can
Yes.
come?
Yes.
But I'm asking that
Physically, you're asking physically. Yeah.
like,
Yeah. But
how many times are possible? Like inequivalent times are possible. You can
yeah,
ask on that side.
you could ask on this side. And but first, the question of how many inequivalent daggers are there?
That I think it's too many. I mean, I think one. Like,
But I wonder if we really were very careful about that. There are a lot, but you know, there's some equivalences. Right. Firstly, of course, you see, the different daggers could be like this, right? There's time here, but that can be rotated by Lorentz transformation.
oh, those types of symmetries
Should be removed. Okay. After doing that carefully, whether there are really inequivalent things, it's something to look at. Yeah. Right. So those we would not consider non-trivial, right? Yes.
They are not equivalent up to this. Like in radial quantization, the condition for hermeticity is like pi dagger is pi of 1 by n.
Yes. Yes. Yes.
So those are equivalent, right? Or you are saying those are different.
No. Those are equivalent. That what you just said was taking the cylinder condition and putting it on the plane. That is equivalent. But on the plane, there is a separate hermeticity condition. Just with time. That is inequivalent to what you got from the cylinder.
So on the plane, the time now is vertical,
vertical rather than radial, and that's different. It's completely different. You see, it's completely different because they give you different Hilbert spaces. One of them gives you a Hilbert space that's a continuum. That's the one in which time is up. The second one gives you a Hilbert space that is discrete because the Hilbert space on the cylinder. If we take cylinder to plane and then set time to be vertical. Yeah. So yes, the 2D cylinder. Yes. And now what is your last question? Yeah. So if you take the cylinder to the plane, the Hamiltonian on the cylinder is not the Hamiltonian on the plane. It's the generator of scale transformations. Right? So you can, now it's a question of what you analytically continue. If you analytically continue the radius, then you're working with the cylinder time. If you analytically continue time, tau, you know, this vertical time. What do you mean there is no vertical time? I mean, in the Euclidean path integral, there was a path integral on the plane. And there's a time that goes vertical. XY axis, the Y. Yeah, you could just simply continue the Y axis to I times T. I didn't even understand what you just said, but vertical means plane up. Y axis, you got it. Yeah, you got it, right? So that's what we would normally do in a quantum field theory. When you study quantum field theory 1 or 2, it's not like Tuhin comes up and says, now let's make radius time, right? Yeah. Yeah. What?
Sorry. So this is like, you know, you have a two plane, XY plane.
Yes.
And you made Y axis as time.
Yes.
And in the second case, you got
R is equal to e to the power tau and make tau.
That you made R as the time.
Log R is time. Yes.
Log R as time. Now you can take various coordinate systems like hyperbolic slicing instead of circular slicing, and then you take that radius to be time.
Yes.
And then
yes.
what kind of things?
Yes. Good question. There should be a symmetry, but he was careful to look at hyperbolic slicing, for instance.
Yeah.
Which, but hyperbolic of the plane. Yeah, yeah. It should be that your time is generated by a killing vector. That's why the radial quantization is something that is well defined in a CFT. The problem with radial quantization, this is really not the topic, but anyway, but the problem with radial quantization, if you try it in a quantum field theory, is that it can lead to divergence at short distance. You know, so when you do something formal, especially when there is a point on your space in which funny things are happening, you have to be sure that nothing funny is actually happening. And with radial quantization, there's a point in space which funny things are happening, namely the origin, because all points on the sphere, okay, all points at t equals minus infinity go to one point of the plane. So something odd here, right? Because on the cylinder, it looked like it was a space, it was mapped into a single point. And to make sure that that doesn't lead to problems like divergences and so on is an issue. And conformal invariance ensures that that doesn't happen. Right? But with ordinary quantum field theories, that can and sometimes does happen. Okay, I can't even remember why we started this. Other dagger, thanks. Okay, but good. We will, when we study superconformal field theories, we'll come back to this discussion. It's great to have these discussions. Yeah, but let's move on. Okay, excellent. Fine. So, but where were we? Yeah. So we were moving on to d equals 3. Okay. So in d equals 3, what was our algebra? Well, in d equals 3, there's no chirality. In d equals 3, Spinors, Lorentzian d equals 3. Spinors were nice, real, not pseudo-real. So no omega aj. So from this formal point of view, the algebra was much simpler. In fact, it's the first algebra we wrote down, I think, because it was the simplest. Okay, and this was P/C. Okay, now let's work this out. P/, now what is this? P/ was this, except there's also P/ is this, except that there's also now P3. So we have P3, P1 plus P0, P1 minus P0, and minus P3. Now we're supposed to take this and multiply it with C. So 0 minus 1, 1, 0. Okay, so let's do that multiplication. So we get, we can have a central charge. Let's add that percentage. Thank you. Zijc alpha. Let's add that percentage. Add that percentage. Thank you. Okay, and so sort of out of white chalk, but okay. I hope the camera is capturing this. Okay, we'll try to. Okay, but it's better with white. This is a bit duller. Yeah, I'll try to use white as much as possible. Yeah. Okay. Yeah. So if we multiply this out, we get P1 plus P0, P1 plus P0, and then next one is minus P3. Next one is minus P3, and next one is P0 minus P1. What? This is P/C. Okay, so ignoring the central charge for a moment, what have we got? Okay, if we ignore central charge for a moment, what have we got? We've got Qi. I'll continue to call the components of Q, Q plus and Q minus. So Q I is equal to qi plus qi minus. Okay, so this tells us that q plus j is equal to delta ij p1 plus p0 as before, as in d equals to. There is a delta ij here. And q minus j is equal to delta ij p1 minus, sorry, p0 minus p1. Actually, it's very important that it's p0, that these two p0s have the same sign, because otherwise we'd land up with an inconsistency. If something would be both positive and negative, and we'd drop it. Okay, and then we also get that q plus I, q minus j. I should have written this in a place where there was more place to add in the central charge, but let's first look at this. Okay, is equal to delta ij, and then plus and minus. So we want the top guy, but that's the same as plus, minus plus, it's p3. Note the fact that this p, what, where is it? Yeah, minus p3. Minus p3. Thank you. The fact that these two are the same was a consistency condition. Because q plus q minus anti-commutator is same as q minus q plus anti-commutator. All these things, this was the thing that we checked with transposition, right? Where is C alpha beta? That's the Zij term. We've ignored that. This is P slash C. So far, so good. Now we're adding now we have to add in as both, what is your name again, please? Vineet. Sorry. Vineet and Sunil both have pointed out that we've been very rash. We've ignored central charges. So let's add. Okay. What is central charge? Well, that we've seen many times. So 0, -1, 1, 0. And then the Zij. Okay. So that tells us that the full algebra is qi alpha qj beta. That full algebra is delta ij times what we had. This p1 plus p0. Let's call it p0 plus p1. 0, 0, p0 minus p1. And sorry, with the p3s. Minus p3 minus zij or plus, let's say, Zij into 0, -1, 1, 0. Okay. Now, this Zij being antisymmetric compensates for the antisymmetric of this guy. Otherwise, we would have had an inconsistent algebra. Right? When we interchanged I and j and alpha and beta, we would have got inconsistency. Okay. And you can now break this up into components, right? Okay. The plus minus thing changes. The plus minus thing changes. Instead of having just a P3, it also has a minus Zij, exactly. This is plus minus, and then Ij, and then the other one has a plus Zij, plus P3 Zij. Zji. And the fact that they are negative of each other tells you that it's consistent. Okay, excellent, excellent. So notice once again in this three-dimensional algebra, what was the hermiticity condition? Q plus I dagger was Q plus, Q minus I dagger was Q minus. It's the reality condition. Okay, excellent. Excellent. Right. Now I wanted to do one more dimension that was a bit less trivial. I wanted to do 4 dimensions, but I'm wondering if we will have the time to finish it today. Let us start. Let us try. Please. I could hear. Sorry, say. Yes. Mm. 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 Yes. So Kanu is pointing out that we checked the consistency of these by treating the spinors as being numbers. Okay. Now, his question is, when we take dagger, will it change anything? It changes nothing, right? Because you had anti-commutative. Anti-commutative. Come, let's do it. AB plus BA dagger. Okay. We either change or don't change. We will get the same thing. Because both terms are there. Okay. At the moment, we were treating them as just pure numbers. But it's true that sometimes inside a path integral, we will need to do what you're doing. So it's interesting that it also works out. Okay, but at the moment we were thinking of them as, yeah, but you're right. Okay. Okay. Yeah. Basically, Kanu's question was more general. It was the following, that when we take operators, when we take a number and make it number and star, and we want to replace that by operator and dagger. Okay. When we do it with operators, we also interchange order. Also interchange, because these Grassmann things should really be thought of as operators. Grassmann numbers are not real things, right? I mean, but they can be implemented by matrices. Therefore, they're operators, and therefore they obey all the rules of operators. Right? So this, you know, if you have A, B star for numbers, we could say B star, A star, but we could also say A star, B star, because for their numbers, they commute. When we have operators, we need to put the dagger with the right order. Okay, as long as we have, in this algebra, the star and the end, there was no ambiguity, basically. Okay, good. Excellent. Let's keep going. Let's keep going. I'm just wondering whether we'll miss lunch if we start 4 dimensions. Let me start anyway. Okay. I'm doing all this so that the formal analysis we do in the next class for representation theory makes sense. Okay. In the sense that we will do some formal analysis, find some representation theory, but I want you to be able to think of what we're doing, not just do it like a map. That's wrong. But okay. Okay. So, yeah. Okay, so let's just get one more dimension sort of a bit explicit. Okay, so we want to set up spinors in 4 dimensions. Okay, we want to set up spinors in 4 dimensions, and let's see how it goes. So our gamma 1 was equal to sigma 1 times sigma 3. Our gamma 2 is equal to identity times sigma 1. This was Euclidean for a moment. Okay, was identity times sigma 1, where our gamma 3 was equal to sigma 2 times sigma 3. And our gamma 4 was equal to identity times sigma 2. Okay, so let's just for 2 minutes, let's work out the Euclidean business Now, you remember we showed in every dimension, and it's very obvious here. It's a product of all these gammas. Sigma 1 times identity times sigma 2 times identity. So it's sigma 3. Sigma 3 times sigma 1 times sigma 3 times sigma 2, sigma 3 times sigma 3 is 1, and the other two gives sigma 3. And then there were some i's, but they were always chosen so as to, please come. The i's were always chosen so as to make sure that gamma d plus 1 squared to 1. So we just choose that by hand. So that's equal to sigma 3 times sigma 3. All good? Okay. Now, how do we think of spinors? Okay, spinors are of course 4 components in this particular dimension, but it's convenient for us to think of it as in a tensor product space, 2 cross 2, right? So one way of thinking of it is follows. In 2 dimensions, we worked with just a 2 component spinor, which was really, when we wrote alpha beta, one way we could have thought of it as alpha times plus beta times minus, where plus was the spinor which was 1 0, and minus was the spinor that was 0 1. Okay, so more generally now we can think of spinors in the following way. Okay, in this dimension we will have alpha plus plus times plus 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 alpha plus minus times plus minus. Okay, times plus alpha minus plus times minus plus plus alpha minus minus times minus minus. Okay, these are of course just the tensor products of spinors, of these two component spinors. Right? All clear, right? Okay, great. So we will use these as the coefficients that parameterize our spinor. And when we work out the reality conditions, we will see what happens to the complex conjugate of these parameters, just like we did for alpha and beta, to try to be completely abstract, completely explicit. Okay, great. So now let's see what we get for the reality condition for these spinors. Okay, but this is going to, in Euclidean, it will be real, because you know SO4 is SU2 times SU2. It will in fact will be, oh sorry, pseudo-real, but chiral. Pseudo-real, each spinor, yes, there will be a real, sorry, you're right, pseudo-real but chiral. Okay, and so the chiral spinor will go back to itself. The anti-chiral spinor will go back to itself, but in a pseudo-real way. This is what we should expect, as you said. Okay, so what was the chirality matrix here? This was sigma 3 times sigma 3. So a chiral spinor is one with either an even number of minuses. So the chiral spinor is this guy and this guy. Whereas the anti-chiral spinor is with an odd number of minuses. So it's this guy and this guy. Right? Because it's a question of whether this guy, notice, of course, I hope it's clear, that plus means eigenvalue 1 under this sigma 3, and minus means eigenvalue -1 under this sigma. Similarly for the other guy. Okay, so plus plus has eigenvalue 1 because it's plus 1 times 1. Whereas minus minus has eigenvalue 1 also because it's -1 times -1. Whereas the other two have eigenvalue -1, and therefore anti-chiral spinors. Clear? Okay, so this was the chiral spinor and this was the anti-chiral spinor. Okay, now we will look at our reality condition. So our reality condition was that psi was equal to C times psi star, Euclidean so far. Okay, so psi was equal to C times psi star. Yes, 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 yes. We're going to check whether this has solutions or not. So we will find that we will need to put this omega. First thing we're going to check is whether this, whether this mixes up the chiral and anti-chiral part, or keeps it within chiral and chiral. And then we will check whether this has solutions. So you're right, we should find that it doesn't. You're going to do that explicitly. Okay. So psi is equal to C times psi star. Well, let's see. So what was C? Now, so this is our basis of spinors. Okay. So we have C, which was, now what was C? C was sigma 3 times sigma 4 as the gamma 3 times gamma 4, which is sigma 2 times I times sigma 1. I'm wondering whether that's okay. Let's just minus I times sigma 1. I'll keep the minus I, though it will matter for nothing. So this is equal to C. C was equal to this. I'm multiplying in each tensor product factor, sigma 2 times I and sigma 3 times sigma 2, which is minus I times sigma 1. The minus I will matter for nothing, but I'll keep it just so that you don't get confused. Okay. So now what? So now let's see. Let us start with a spinor which was this. This was our psi. Okay, psi star is just this with all components starred. Okay, and now we have to act with C on this. Okay, so now let's see, what does C do? C acts as sigma 2 in the first factor. Okay, and it acts as sigma 1 in the second factor. So we have to keep our wits about us. So remember that sigma 2 times plus is equal to minus I times minus, whereas sigma 2 times minus is equal to I times plus. Okay, sigma 1 times plus was equal to minus, and sigma 1 times minus was equal to plus. This is clear, right? Sigma 2 plus is sigma 2. Oh, yeah, you're probably right. Sorry. 0 minus I 0. You're right. Thank you. Minus and plus. Thank you. Right, because if you apply on 0 1, which was minus, you get minus I times 1 0, which is plus. Plus minus. Yes. Okay. So we'll use these rules now to find out what is the new coefficient. Okay. So we will get, so acting with C on this, what do we get? We get C was this guy. Okay. So let's act on this fellow. That gives us alpha plus plus star dear customer. Okay. Alpha plus plus star, when we act on this plus becomes a minus, this plus becomes a minus, of course. And now we have to keep our wits about us about the signs. So sigma 2 plus gave us I. This gives us no sign, and there was a minus I, so that's 1. Okay. Plus. Now let's act on the next guy. Plus minus alpha plus minus star. Okay, let's do act on alpha plus minus star. We will get on plus gives us, I'm getting minus plus with no sign. No sign. Please check. Alpha minus plus star, and now I'm getting plus minus but with a sign, and I get a minus alpha minus 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 star gives you an with a plus plus and with a minus sign. Please check. Okay. Therefore, our reality condition is as follows. Alpha minus minus is equal to alpha plus plus star. Our attempt at putting reality conditions is as follows. What? Alpha minus minus was alpha plus plus star. Okay. And alpha, and now we see the problem. Alpha plus plus is equal to minus alpha minus minus star. Okay. Similarly, alpha plus minus was this guy, which was equal to minus alpha minus plus star, whereas alpha minus plus was equal to alpha plus minus star. Clearly, two things to note about these equations. Two things to note about these equations. First thing to note about these equations is that they're not mixing chiral with anti-chiral. This is consistent with our general theory. In this dimension, because n is even in Euclidean space, okay, it does not mix chiral with anti-chiral. Right? The second thing to note is that these conditions are clearly not consistent, because you take the complex conjugate of the first equation and each pair, it's inconsistent with the second equation. Okay, so we see from this point of view how we are forced to impose pseudo reality conditions in four-dimensional space Euclidean. Okay, next class we'll work out the Lorentzian algebra and work out the supersymmetry algebra in great detail in 4 dimensions. So you see it very, very explicitly. Then we will turn in the next class to doing working out the general representation theory of supersymmetry with all this sort of in your mind. Okay.